noir plasma chrome bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.
This website makes learning so easy. I found all my resources here.
Like what you share.
String theory suggests that the universe is not made of particles, but of tiny, vibrating strings of energy, harmonizing to create all reality.
Bosonic string theory requires 26 dimensions, but it predicts unstable tachyons with imaginary mass.
Welcome to the Explainer. Today, we're looking at the 1960s Model T of modern physics, bosonic string theory. Just like Henry Ford's original Model T automobile, this theory was absolutely brilliant, totally foundational, and, well, ultimately filled with some pretty dramatic mechanical flaws. But it was the very first attempt to describe the fundamental nature of reality using vibrating one-dimensional strings instead of just tiny point particles. And, while it's definitely been superseded, understanding this original model is literally essential if you want to grasp the complex machinery of modern theoretical physics. Let's get into it.
Okay, let's dive into this. Here's our roadmap for today. First, the original string theory. Second, problems with the theory. Third, types of bosonic strings. Fourth, math and path integrals. And finally, number 5, topologies genus 0 and 1.
So, Section 1, the original string theory. Let's establish exactly what this foundational framework is and where it actually came from.
Bosonic string theory was developed back in the late 1960s, making it the original flavor of string theory. It gets its name for a really straightforward reason. Its spectrum contains only bosons. If you remember your particle physics, bosons are the force-carrying particles, like photons or gluons. Think about how wild that is for a second. This early framework essentially tried to build the entire universe out of vibrating strings that only manifested as these force-carrying particles. It was trying to explain the whole shebang without any of the actual building blocks of matter that you and I interact with every single day. Crazy, right?
Now, you might be wondering, okay, if it's from the 60s, what replaced it? Well, in the 1980s, physicists discovered supersymmetry in the context of strings, which led to a brand new version called superstring theory. That quickly became the real focus. But here's the thing. Despite being sidelined, bosonic string theory remains a highly useful model. It acts as an incredible theoretical sandbox. Physicists literally still use this 1960s theory today because the math is just easier to practice on. It helps us understand the general features of perturbative string theory. In fact, a lot of the theoretical headaches that plague modern superstrings can actually be found and studied right here in these simpler bosonic strings.
That brings us to Section 2, problems with the theory. If it was such an amazing starting point, why exactly did we have to abandon it? Let's look at those mechanical flaws.
Now, what's really interesting about this is that the theory has 3 fatal physical flaws. First, as we just mentioned, it predicts only bosons, no fermions. The problem there? Basically, all the physical matter in our universe is made of fermions, like the electrons and quarks. You can't really have a theory of everything that just leaves out all the matter, right? Second, and this is where it gets super dramatic, it predicts a mode of the string with an imaginary mass. This is known as a tachyon. In physics, imaginary mass is absolutely catastrophic. It means the theory is highly unstable, prone to a runaway process called tachyon condensation. Just bad news. And third, in a general space-time dimension, it displays massive mathematical inconsistencies because of something called the conformal anomaly.
But physicists didn't just throw their hands up when they hit that conformal anomaly. A physicist named Claude Lovelace noticed something incredible.
The anomaly actually cancels itself out, but only if the theory exists in exactly 26 dimensions. No joke. 25 dimensions of space and 1 dimension of time. This is known as the critical dimension for the theory. Now, we obviously don't see 26 dimensions around us when we walk down the street. So how does the theory account for this? Well, it proposes that the excess 22 dimensions are folded up or compactified. To visualize this, think of a garden hose. From far away, it just looks like a one-dimensional line, but when you get up close, you see it has a curled-up circular dimension around it. String theory suggests those extra 22 dimensions are curled up into a microscopic shape, kind of like a small torus, leaving only our familiar 4 dimensions of space-time visible. It's a brilliant workaround.
Moving right along to Section 3, Types of Bosonic Strings. Let's categorize the variations within this wild 26-dimensional framework.
So there are 4 possible bosonic string theories, and they depend on basically 2 things: whether open strings are allowed alongside closed strings, and whether the strings have a specific orientation. A specific orientation just means that 2 strings can only merge if they have the same orientation on their world sheet. Now, if a theory does allow open strings, it has to include closed strings too, because open strings are thought of as having their endpoints fixed on something called a D25 brane. Think of a D25 brane as this physical surface that literally fills all of space-time, acting like a giant canvas that these open strings are firmly pinned to. Notice that across all 4 of these types, they all share that problematic negative energy tachyon and a massless graviton. For the most part, though, physicists tend to focus their energy on the closed-oriented theory. Let's transition to Section 4, Math and Path Integrals. We're going to pop the mathematical hood and see how this theory actually works.
So the absolutely crucial point here is that bosonic string theory is defined mathematically by the path integral quantization of the Polyakov action. I know, that sounds dense, but in the simplest terms, imagine a string moving through time. As it moves, it sweeps out a 2-dimensional surface called a world sheet. The Polyakov action basically contains a field on this world sheet that describes exactly how the string is embedded into that massive, mind-bending 25 plus 1-dimensional spacetime we were just talking about.
The math here actually flows through a really logical sequence. Step 1, you embed the string in the 2060 spacetime using a Minkowski metric. Step 2, you perform what's called a Wick rotation, which brings this over to a Euclidean metric. Step 3, you have to add a counter term, a purely topological term proportional to the Euler characteristic, just to deal with Weyl symmetry breaking. And finally, step 4. The symmetry group here is so massive that it actually overcounts things, so you have to mathematically quotient away diffeomorphisms and Weyl transformations. Now, if that sounds like an avalanche of terminology, don't worry. The big takeaway is that this brilliant sequence of steps lets physicists tame the infinite, chaotic possibilities of a moving string, reducing them down to a finite, solvable geometric space, which we call the moduli space.
That brings us to our final section, number 5, topologies genus 0 and 1. Let's look at the actual topological shapes these integrals sum over. The perturbative series in this math is expressed as a discrete sum over possible topologies. These are indexed by a genus, represented by the letter H. Let's compare the first 2, and you'll see a massive physical jump in the shape. At H equals 0, we have the base tree level. This is essentially a simple sphere. Down here, the cosmological constant vanishes, and the 4-point function for the scattering of 4 tachyons yields the Shapiro-Virasoro amplitude. Honestly, it's relatively well behaved. But jump to H equals 1, and the shape transforms into a torus, or a donut shape. This corresponds to the 1-loop level. Because of this jump in shape, the math gets exponentially harder and incredibly complex. You have to integrate over a fundamental domain for the modular group, and it utilizes this absolute beast of a formula called the Dedekind eta function. And this brilliantly brings us full circle to the ultimate fate of the theory. When you actually try to compute that H equals 1 torus integral, it diverges. The math literally breaks down. Why? Well, it diverges entirely because of the presence of the tachyon. Remember that imaginary mass particle we flagged as a massive catastrophe back in the problem section? It rears its head right here in the advanced mathematics, directly reflecting the instability of the perturbative vacuum. The math perfectly and tragically proves the physical flaw. Which brings us to the end of our explainer. Bosonic string theory was a spectacular leap of imagination, a 26-dimensional universe made of vibrating strings. And even though its own path integrals prove it to be fundamentally unstable, it laid the absolute essential groundwork for everything that followed in the field. It really makes you wonder,
If this mathematically unstable Model T gave us such profound insights into the underlying structure of reality, what incredible dimensional secrets might its supersymmetrical successor still hold, just waiting for us to discover?
Like what you shares.
This website makes learning so easy. I found all my resources here.
Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.